Good afternoon, everybody. Welcome to SDA's webinar on Nastran Solution 200 Design Optimization. I'm David Cross, and today I'll give you a brief introduction to Solution 200 and optimization in general. So first, I'll give you a little background on our company, SDA, Structural Design and Analysis, and then we'll talk about what is design optimization. And then we'll go through some demonstrations. I have two example problems that we'll go through. The first is thickness optimization of a stiffened rectangular plate, and then thickness optimization of a wing with buckling constraints. So throughout these two demonstrations, I'll talk about how to set up the optimization model in FEMAP, how to post-process the optimization results, some general considerations, things like how to add buckling constraints, how to adjust the optimizer's parameters to improve convergence. And lastly, I'll also make some quick comparisons to Hypersizer, which is another software I'll mention here in a minute. And then I'll just provide you with some additional resources. So SDA was founded in 1997, and we provide expert aerospace structural analysis services. We serve a variety of industries. We specialize in composites and developing strong, lightweight structures that are readily manufacturable. We provide typical support programs, support for programs such as small to large UAVs, manned and unmanned spacecraft, naval structures, and we have a team of over a dozen engineers with varying levels of degrees, BS, MS, and PhD, and we're located out of Sterling, Virginia. So some of our partnerships are with Siemens. We are a value-added reseller specializing in FEMAP with NX Nastran, which we'll be talking about today, NX Nastran Enterprise, FiberSim, and Solid Edge. And we're also a partner with Collier Research Corporation and a reseller for their software package, Hypersizer, which is a structural analysis and optimization package for composite and metallic structures. And I'll also talk a little bit about that today. So just to give you an idea of some of the projects we've worked on in the past, everything from UAVs such as the AAI Shadow and Aerosonde, Lockheed Constellation Restoration for Lufthansa, and then a number of spacecraft projects from the Composite Crew Module to the James Webb Space Telescope, Orion Heat Shield Mass Reduction for the NESC, and Orion Crew Module with Lockheed, and we worked on the W-FIRST telescope for Goddard. Okay, so what is design optimization? Basically, fundamentally, an optimizer is a formal plan or algorithm used to search for a best design. What constitutes a best design really depends on how the user defines the optimization problem. So typical parameters that must be defined are an objective function, design variables, and design constraints. So the objective function could be to minimize mass or minimize cost. Design variables, as you'll see today, will be our plate thicknesses, but it could also be other geometric parameters that define the shape of your structure. Constraints are typically you're constraining a response of your analysis, so stress constraints, displacement constraints, frequency constraints, etc. So NX Nastran uses a gradient-based algorithm, and a gradient-based algorithm essentially uses design sensitivities to find the best search direction within your design space. So design sensitivity is essentially the rate of change of an analysis response with respect to changes in the design variables. So this little cartoon image on the right is actually from the NX Nastran Optimization User's Manual. And so our objective function is this contour plot in 2D, and the axes X1 and X2 are our design variables. So we have two design variables in this case. So if we started the design point over here on our contour plot, our steepest descent direction is found by the optimizer through design sensitivities. And so you'll notice that that direction is perpendicular to the contour that we're lying on. And so it'll step in that steepest descent direction. It'll search for a minimum in that direction, and it'll reevaluate the design sensitivities and find a new steepest direction. So that's essentially what NX Nastran, the design optimization solution sequence, is doing in the background. This is a cartoon of a linear method. You can actually use a higher order method called sequential quadratic programming in Nastran, which I'll mention briefly. But that's basically what it's doing. It's trying to find and search for the best design within your design space. And it finds a local optimum, which is not necessarily the global optimum. And I'll talk about that as we move forward as well. So to give you an idea of how the model is set up in Nastran, is basically through your property cards. So let me first say that Solution 200 can be used with static analysis, normal modes, buckling, directed modal frequency, modal transient, acoustic, aeroelastic, all of these. But FEMAP only supports statics and normal modes at this time. So we'll focus there. I'm actually going to show you how to edit the run decks to add buckling. And then basically how the Nastran cards, what they look like, and what options you have. The design variables are defined in relation to property or material entries, and your design constraints are defined in relation to analysis responses. So basically any field on a property or material card can be set as a design variable, although this is limited in FEMAP. Shape variables, which allow nodes to move, can also be defined, but this is not supported in FEMAP. And so here are just some, if you want to look into this further in the quick reference guide or in the optimization solution manual, some of the Nastran cards that we'll be using in Solution 200. So the first example problem is the stiffened plate, and I'm going to come into FEMAP here. So we have a stiffened plate, and I've broken up the properties here by pockets and by the fillet regions, and so there's 42 different properties, so we'll optimize this according to 42 thicknesses. We have simply supported edges and a pressure load on the underside of this stiffened plate. And so we're going to, if I show you the analysis results for just static analysis, what we see is that we have a deformation of 0.148 inches and a peak stress of 15 KSI. So what I'm going to do is show you how to set up Solution 200 to optimize the mass of this, minimize the mass, subject to a stress constraint of 25 KSI and a vertical or Z displacement, Z translation of 0.35 inches. So first we set up model optimization. And so this is where we're going to define all of our parameters. So goal is our design objective, and we're going to minimize weight, and that's the only option. And then we need to set a maximum number of design cycles. The default is 5. For this, I would always probably put it at 15 for simple problems. More complicated problems go up on the order of 30, 50. That'll come with experience of what you need. And your results will tell you if you have enough or not. So that's all we need to do there. So now we need to vary. We need to set our design variables. So first, here are the options that FEMAP supports. You can set design variables as the rod area, torsional constant, the bar area, your area moments of inertia, torsional constant, and plate thickness. Siemens has decided to only support these because these are the most commonly used and the simplest. If they start having users that want to use some of the additional features that Nastran allows and they get a lot of requests, then they might implement some of those in future releases. So that's something to keep in mind. So we're going to adjust plate thicknesses, and we're going to set a maximum. We'll set it of 0.5 and 0.05. Okay, and then put our cursor in property, and we're going to select multiple. We're going to select all 42 properties. Okay. So now you see we've got design variables set up that can vary from 0.05 inches to 0.5 inches for all of our properties. And now limit, this is where we define our design constraints. So you can see you can set up constraints for responses of all these different output vectors that we typically have for a linear static analysis run or a normal modes run. So we're going to constrain the Z displacement, and we'll set a maximum of 0.35. And now this is important. The minimum, really, we don't expect to have any negative displacement in the Z direction for this load case. But we don't want to have a constraint at 0, because some of these nodes are going to be displacing about 0. So if we have that, then we'll end up with an active constraint, and it'll interfere with the optimizer. So since we don't care about the lower bound, I'm just going to set it to negative 0.35, which we won't come close to. And that way we know it won't interfere. So node, I'm going to select multiple. I'm going to select all. Okay. So now we've got all of our nodal displacement constraints.
Muted.
And then we can define our stress constraint. So I'm just going to do plate von Mises stress. And we'll set a maximum of 25 KSI. And in this instance, I'm just going to leave this blank. I think it defaults to 0. So property, multiple, select all. So now we're constraining all the properties. So it's sizing by property. So the property thickness will be allowed to vary so long as the peak stress within the elements of that property don't exceed 25 KSI. So that's all we need to do for the model optimization setup. But now we need to set up our analysis. So if we go to our analysis manager, manage, new, and we select design optimization, and I will call it optimization. And this is going to look a lot like you're setting up a linear static analysis. So we'll just click next. All the defaults are good here. So this is the one feature that's different, design optimization options, the analysis type you want to include. So here we have our two options that FEMAP supports, static or normal modes. We're doing static, so I just select next. And again, all the defaults are good. We've got our active constraints and our active load set and output to the full model. Okay. So the weird thing there is that we don't reference what we just set up under model optimization. The design optimization analysis, when FEMAP creates the run deck, it'll automatically pull all those parameters that we set and put them into the run deck. So if we preview input, here we can see we have a static analysis. So design objective, we're going to minimize. We have one design subcase. And if we go down here a little bit, here this is the d-optim parameter, design variable max iterations 15, just to give you an idea. And you can see it auto-filled in our definition. So here we have our objective function. We're going to minimize weight. We have our first design variable ranging from 0.05 to 0.5. And this is what I meant by it references the property cards. So you have a DV property relation card, and you call out the P-shell card, the P-shell ID, and then the field on the P-shell card that is your design variable. So thickness is the fourth field on a P-shell card, right? And then this is the design variable ID, which references our design variable card. So that's how the design variables get called out, and it's similar for the design constraints. But everything's ready to go, so we set it up. It's fairly straightforward, and now we can hit analyze, and it should go pretty quick. So you can see it's going through the design cycles, design cycle 2, design cycle 3, 6, and it's done. Okay. So when you run it by default, you'll get one additional output set, and that is a linear static analysis of the optimum solution. So I always just look at that first, and what we see is we've got 24.97 KSI is our peak stress, so that's bumping right up against our stress constraint, so that's good. That's a good indication. And then we have a max deformation of 0.35 inches, so another good indication. And so as I'm looking through here, I see a lot of properties with red elements, which is indicating I'm bumping up on my stress constraint for those properties. it looks like all of these are deforming around the 0.35 inches or close to it, so that's good. But then all the stiffeners, right, which have low stress and low deformation, well, when I look at my optimization results, I would expect to see that they are at minimum gauge. So the first thing we can do is it'll also output and create functions under model functions. If I scroll down here, I can highlight design objective and max value constraint, right click, show. It should pull up my charting pane. Here we go. And so our design objective, you can see it's flatlining. Our mass is decreasing slightly, right? And we have a max value of our constraint. So it starts out negative. What that implies is we started, I forgot to mention that we started everything at a plate thickness of 0.1 inches, right? And we knew all of our constraints were satisfied. We were under the 25 KSI and under the 0.35 inches. So negative constraint means you have a feasible design. And it goes up, it gets to a positive constraint, which means it's infeasible, comes back down, and then we converge to 0. So that's what we want to see. We want to see these going flat. It means our design isn't changing much. It means we're converging, and it means we have an active constraint. So now I want to go into the F06 file really quick. And show you what to expect and what to look for in the F06. So we scroll down to the bottom. If you go up, we see run terminated due to hard convergence to an optimum at cycle number 7. So that's good. It converged. If it doesn't converge, you'll get some sort of error message, and we'll see that in a little bit. And then it shows you your design variable iterations here and the thicknesses as they change. And there's some more information if you go through that about what was happening. So we can also plot our design variables. If you highlight all the design variables and select show, display in charting pane, yes, and this is annoying, the default is the legend. So if you go to chart options, you can select right outside and center to set where you want your legend to go. So here we see all the design variables. All our plate thicknesses started at 0.1 inches. And all of them came down. A lot of them came to min gauge. Some of them did not go to min gauge, which we would expect. And they're all flatlining, which says they're converging. So this ran well. We found an optimum. And I'm going to go back to the PowerPoint quickly. So here's, for those interested, the mathematical statement for our optimization problem. The initial mass was 22.7 pounds. Here's our plot again. Here's the thickness distribution. So we do see min gauge in our ribs, as I suggested we should. And our optimized mass is 14 pounds. So we decreased by 36%. So pretty good result. And here's just showing we were at the 25 KSI and 0.35. So then what I wanted to do was to see what would happen if we initialized our design at a different design point. What if everything started at min gauge? So I started everything at min gauge, and as you can imagine, my stress constraints were violated, my deformation constraints were violated, and that's indicated here by a positive max value of constraint. But it did converge, this time in just 5 cycles, to a very similar weight of 14.6 pounds. That's a nearly identical optimum. So this was very good behavior. This means that it was a simple problem. The optimizer was able to converge smoothly and nicely. We started at different points in the design, and the optimizer still found the same design. So on the right here, this is kind of a teaser because I'm not going to get into a lot of details about Hypersizer, but I just do want to mention that it is a software that we are a reseller for, and it's very powerful, but it goes about optimization in a very different way. Basically, you run your finite element analysis in Nastran or some other finite element service, and you can import those analysis run decks into Hypersizer. and it gets a nice fin model. It sort of auto sets up a bunch of stuff. And then you can define, okay, is it a metallic, is it a composite? You can define the properties automatically come in as separate components. You can define all sorts of failure analysis to use when optimizing, but it uses all closed form solutions and some iterative numerical solutions that aren't finite element analysis, but are based on experimental data and things of that nature. So it's very capable and fast, and it'll search through your entire design space, and it looks at all the possible design candidates and tells you the best one. But as it adjusts thicknesses, it's keeping the same finite element loads in the structure. So it's important that you go back and iterate with FEA. You import your new thicknesses, run FEA again to allow the loads to redistribute, bring them back into Hypersizer, and rerun until your load distribution converges and your design converges. So I was able to find a very similar design. It was off by, you know, 1,000, on the order of a couple thousandths of an inch for each of the properties at about 14 pounds. But I don't know if I fully converged. I may have needed more iterations with FEA. And the Nastran convergence tolerance is it defaults to 1e-3. So if I crank that down and use a tighter convergence tolerance, I might be able to squeeze a little more mass out of it. So here are just the thicknesses. Okay, so now I wanted to talk about the wing problem. And specifically, we're going to look at buckling. So we have a metallic wing with a uniform pressure load on the bottom surface. We've got skin, spars, ribs, and some stringers. We're going to look at stress constraints, buckling constraints, and lower and upper bounds. Okay, so let me get back into FEMAP. All right. So let me just show you our initial static analysis or static buckling results. So you can see here that it's displacing about 8 inches. Let me adjust this scale to actual. And I'll tell you that the stress is 31 KSIs in this is peak stress. What I'm mostly interested in this problem is the buckling. So we have a buckling value of 0.5. So that means that half of 50%, 52% of our load, we're going to buckle. So we'd like to see that get above 1 at a minimum. So our initial design isn't good, and really the buckling is going to drive this design, not so much the stress. So let me go into model optimization. So here I set the maximum number of design cycles to 35. Okay, a little bit more because it's a more complicated problem and there are more design variables. There are 63 properties that we're optimizing. We're not going to optimize the stringers or the spar caps in this case. So I decided to vary the plate thicknesses. The skins, I decided to range from 0.03 to 0.5, and all the ribs and spars from 0.05 to 0.5. So you define these the same way as before. Select plate thickness, plug it in, select, very straightforward. So not much is changing here. For my constraints, I did a stress constraint of 45 KSI, and I already mentioned it's not going to drive the problem. And so that's really all we can do in this model optimization window in this dialog box. And so how do we define the buckling? Well, if I go into, when I set up the analysis, the optimization analysis, same as before, choose design optimization, next, all defaults. So here we need to edit the bulk data to include buckling. So when you go through a buckling analysis, some of you may be familiar with the IGAR-L card. So this is really just defining your buckling method. So 1 is just the buckling method ID. 0.01 and 6 is the range for which I'm looking for buckling eigenvalues. 1 means I'm only interested in the first or the lowest buckling mode. The 0 is some default parameter that's not very important for what we're doing. And then the max is just I'm max normalizing my eigenvectors. So that's pretty straightforward. And really what I did is I ran this buckling analysis. I took the run deck, I copied the IGRL card out of it and pasted it into here. So now we can set up our buckling constraint. So the D response 1 card, right? So the 7000 is just an ID for my response. R7000 is just a label. Lamma means that it's a frequency response, a frequency type response variable. And then the 1 means, so say my buckling analysis resulted in 5 frequencies. The 1 means I'm going to define this response as the first of those 5. So in this case, we only have 1. And then this D constraint card, the 2 references my design subcase. So I'll show you in a minute. Our static analysis is subcase 1, and the buckling is subcase 2. So we have a 2 here. The 7000 references back to my response card, and then the 1.15 means we have a lower bound on our eigenvalue of 1.15. And then this param NASPrint is just a nice feature that you may be interested in when using solution 200. This means I want it to give me output sets at every design iteration, every design cycle. And so that's all we need to do to define our buckling constraint. But we will need to edit the case control section. So again, I choose static analysis, and you can see up here in my analysis window that my subcase 1 I have is static. And so subcase 2, we define it as buckling. We reference our IGRL card. It's subcase 2, and then that's just some output. So fairly simple. Here we have our master constraints, master loads, and our output. And if we preview the input, we can see everything in here again, and everything that we edited. So it's ready to analyze. I went ahead and did it because it takes a little while to run. And I'm going to switch back to the PowerPoint briefly because I already have all the results pulled. But we chart it the same way. We look for the same things. So when we chart our design objectives in our constraint, we see it flatlining, we see it converging, which is good. But notice that our constraint on our buckling eigenvalues is positive. That means it's infeasible. Okay? And if we go into the F06 file, edit with Notepad. There we go. Scroll up. Here we have hard convergence to a best compromise infeasible design. So that means we didn't find a feasible design, which isn't good. Right? And we also see that our design variables are flatlining. So what's happening here is basically that as we go from iteration 21 to 22 to 23, right, our design variables aren't changing much, but our buckling eigenvalues are. And the result is that from one iteration to the next, our eigenmodes are changing. So this is called mode switching. And so the optimizer just doesn't have enough information. So how do we go about fixing this? How can we improve this? So what I did is our model optimization setup is the same. But when we define the run deck, I've been told I lost audio, so we're going to get this cleared up real quick. Okay, I'm told I'm good and everyone can hear me. So we're constraining the first 5 and tracking the first 5. And nothing else changes. So I just defined 5 constraints instead of 1. And what we see is that amongst our first 5 eigenvalues, they're all relatively close to 1.5. Okay. The other thing I did, which if you want more details on, I can provide with you later, is I loosened my default tolerances on the convergence, so that's why we're under 1.15 by a little bit. So I set it to 2% rather than 0.1%. So I loosened it up to give it a little more flexibility, a little more range to find an optimal solution. And that does help it converge, but obviously you have to be aware of what your tolerance is. So we have modes all over the place that are relative to 1.15. So I'm going to go back to the PowerPoint. And so here we see a different mass decrease. It's flatlining, it's converging. And we see that our max constraint comes down in the range of 0 or less than that 2%. And we dropped from 116 pounds to 93 pounds. And we were able to basically optimize our size, our different plate thicknesses, and our different wing sections, and size them down all the way up until they hit their buckling constraint of 1.15. So I tried to do this same problem in Hypersizer, and Hypersizer evaluates buckling margins with closed form solutions. So it does it very differently than what Nastran's doing. So when you import it, it automatically detects, based on your material angles and your property splits, the buckling spans. Okay, so it's going to treat each property or component separately, independently, and it's going to write a buckling margin for each skin and size to that buckling margin for each skin section or skin property. And you have to assume some sort of boundary conditions for this property, and so I assume simply supported conditions, but it has a lot of options for those cases. And then here the iterations with the FEA were critical just because the load distributions were changing quite a bit from one iteration to the next. So here I pulled up, I just plotted the upper skin thicknesses for the Solution 200 run and the Hypersizer run, and you notice they're quite a bit different. And I realized the reason is because I didn't account for the fact that I had stringers in my model when I ran Hypersizer. So that means that my buckling strength was lower for each of these skin sections, and so Hypersizer had to conservatively size the skin, and so that's why we're seeing a little bit thicker. The interesting thing is that it did a better job of allowing my stresses to relax to the 45 KSI bound. And so even though our skin thicknesses are thicker in Hypersizer, the ribs and spars were thinner, and it found a 96-pound optimal solution, although I probably needed to iterate a few more times. So I feel if I went back and did this right and accounted for the stringers, that Hypersizer could get down maybe into the 80s range. And the reason that Solution 200 doesn't do the same thing with the stress is because it's a local gradient-based optimizer. Nastran is allowing for the fact that the spars and ribs have additional thickness that are helping to limit the amount of compression that are going into the skins, whereas Hypersizer treats them all independently and it sizes them independently, and it can search through the whole design space, whereas Nastran is just going to find the closest optimum to where you start. So there's multiple local minima probably within the design space, and they're going to find different ones. Hypersizer will be better at finding the global. So what we've covered today is just a brief introduction of design optimization, the basic fundamental model setup, and general considerations, how to post-process, how to check for convergence, how to account for modal switching. We made some brief comparisons to Hypersizer. There's a lot of details in here, and some viewers may be more familiar with optimization than others. If you're interested in learning more about optimization, Solution 200, Hypersizer, anything that was touched on in this presentation, please contact me or anyone at SDA. We'd love to talk to you and help you out. We can provide training, anything of that nature. So now I'd be glad to take any questions that you might have. Okay. So we have one question here. Can you set up a constraint based on a quantity or percentage of elements exceeding a particular stress? Localized stresses in FEA often require some interpretation. Yeah, that's definitely true. So what by default Nastran was doing is taking the peak elemental stress and sizing to that. One reason I added the fillet region was kind of to account for those localized stresses and to let it size the fillet region separately. Solution 200 does have the capability to define equations to several different responses. You can pull responses not from the property but from the element and then write equations. So you can definitely customize things like that. FEMAP doesn't support it, but there should be enough documentation in the user's manual to get you started there. Okay, well, thank you, everybody. Please, again, if you're interested or want any more details, please contact me. PowerPoint, I think, will be distributed to the registrants or the attendees, and the recording will be posted on YouTube shortly. Or go to webinar shortly. Sorry. Thank you very much.